Good morning. So this particular video is going to look at setting up a resting potential, which is one of the module 5 topics. In particular, looks at 5.1.3c. So in order to do that, we do need to have a quick check-in with your knowledge of your phospholipid bilayer, so your cell membrane, because this is reliant upon that cell membrane in order to set up that resting potential. So just to start with, I'm going to draw your attention to the phospholipids, which are one of the main components of this membrane. So phospholipid is made up of a fatty acid tail, or fatty acid tails, two of them, and a phosphate head. So you can see all of the phosphate heads that are facing outwardly. So this is the inside of the cell. This is the outside of the cell, but they face outwardly relative to the tails because of the tails make up a hydrophobic core. So we have here the phosphate heads, which are described as being hydrophilic, and then we have the fatty acid tails, and those are described as being hydrophobic. Because you have got the charged phosphate head that holds a negative charge, that is a polar, this molecule as a whole is referred to as being amphiphatic. So that means that part of the molecule holds the charge and the other part does not. So the fatty acid tails don't have that charge. So that's why those are going to orientate themselves towards each other, because they are not able to interact with the polar water, which is inside the aqueous solution, which is both outside the cell and inside the cell. So we've got aqueous solution on both sides. So this is quite important. So we've got this situation with the phospholipid bilayer embedded into the phospholipid bilayer. We can see here that we have got a series of proteins. So we have got a sodium potassium pump here, and then there are a series of intrinsic proteins. Now, intrinsic means that they are spanning the length of the membrane, so they are facing both outside and inside of the cell, meaning that they are able to carry molecules both from inside all the way out and from the outside all the way in, as opposed to a molecule that was extrinsic and therefore not spanning all of that membrane. And there are different types of channel protein that we're going to look at today. But just to start us off in terms of thinking about what can and can't pass this membrane, and therefore why we would need to have these channels, key things to always remind yourself of if you're trying to work out if something is able to move across the membrane. Ask yourself the questions: is it large? Is it charged? Now, if your molecule is large or is charged, it will not be able to pass through. And that is why there needs to be a series of channel proteins embedded into the membrane so that the cell is able to selectively move these molecules that are either too big or hold a charge to move them from one side of the membrane to the other. Now, key to setting up our resting potential on our membrane is actually looking at the sodium potassium pump, and that's quite important sort of within its own right, as well as being important relative to the resting potential. So if we come back to the sodium potassium pump to start us off, the sodium potassium pump is really important to any cell, so not just to the membrane of a neuron, but to any of our cells, because it enables the cell to ensure that the sodium levels don't build up within the cell. If sodium levels were allowed to build up within the cell, then that sodium would have an osmotic pull and therefore would draw water into your cell. This would be problematic to the cell because as an animal cell, there is no cell wall, therefore the cell wouldn't become turgid. In fact, it would burst, so cytolysis would take place. So it's quite fundamental to the cell to be able to manage the concentration of the sodium within itself and to actively move these sodiums outside of the cell. And it's using energy within that, so that's one of the things that tells you how the importance of this process. So just to look at this process in detail, so we have our sodium potassium pump here in the corner, and at the moment we can see a situation where actually this pump has just moved sodium from the inside, and it would have just released that sodium because it's opening up to the outside of the cell at the moment. So it's ready for the potassium ions to move into the membrane and to then move those into the inside of the cell. So I'd like to just talk you through that process so that we understand what is happening. So the very first step, and we have to imagine our opening of the protein is actually facing inside at this point in time, would be that your sodium molecules would bind to the carrier protein. Now, when a molecule binds with a protein, that is going to cause a change in its conformational shape. That change in its conformational shape allowed ATP to bind to the carrier protein on the inside of the cell. And ATP is then hydrolyzed into ADP, so adenosine diphosphate, plus inorganic phosphate. Okay, and that's quite important because that's going to lead to another conformational change in the protein, and the opening of this protein now to the outside of the cell, allowing our sodium to move out and enabling the potassium to move in. Now, 3 sodiums, you will have noted, were moved at this point in time. So we've got 3 sodium ions moving outside the cell, and we're now going to have 2 potassium ions moving into this cell. Again, because of the fact that we've got molecules binding with the protein, that is going to then cause a conformational change in the shape of that protein, and subsequently it's going to then enable the potassium to move out of that protein, and it's then going to be released inside of the cell. Now, that phosphate molecule that is released will recombine with ADP and it will form ATP, and the carrier protein will then return to its original shape. For us today, this pump is really important because it is one of the 4 things which helps to maintain a potential difference across a membrane. I'm going to talk you through the 4 different things that are embedded within the membrane or relative to the membrane that are causing this potential difference. First of all, I thought it was important to point out that all cells, so not just your neurons, all cells are going to have a voltage across the plasma membrane, and that voltage is an electrical potential energy. And so your membrane itself is separating the opposite charges. So what we're going to see as we work through this is that we're going to end up with an unequal distribution of our anions and cations, and that's going to lead to a situation where we have a more negative intracellular relative to the extracellular side of our cell. So you've got your intracellular being your inside and your extracellular being your outside. Now, it does vary from cell to cell in terms of what that potential difference would be. And so if you do some reading around, you might recognise that these can range anywhere from -50 to -200 millivolts. However, the resting potential that you need to be aware of is, and your normal resting potential would be sitting at -70 millivolts. Okay, so that's what we are going to look at, how we're going to set up this today. So we'll start with the sodium-potassium pump. Now, when your sodium is being moved to the outside of your cell, there are 3 sodiums that are being moved. When we're moving your potassium to the inside of the cell, there are only 2 potassium. Both of these hold positive charges. So you've got 3 plus moving out and 2 plus moving in. And so straight away, you have got a difference of -1. The second thing to look at with regards to setting up this potential difference across the membrane is the sodium channels. The sodium channels are voltage gated, so that means that they need a change in the voltage of this membrane in order to activate them. And so at the point of our resting potential, our voltage gated channels are going to be closed, our sodium voltage gated channels that is. So I'm just going to block these channels off at the moment, so that they are not able to allow any of that sodium that has been released into the extracellular fluid to flow back in. So we'll just put our sodium here. We've got a sodium voltage gated channel. Our potassium gated channels, though, are open or sometimes described as being leaky. So what we can see here is that our potassium channels are going to enable the flow of the potassium. Now, your potassium has moved into your cell, and therefore we're going to have a situation where we have got an increase. So we've got high levels of potassium inside, and we have got low levels of potassium outside. Therefore, the potassium is going to use facilitated diffusion via your potassium gated channel to move back out of the cell. So we're going to see this outflux of the potassium along its electrochemical gradient. Okay, so we'll see that potassium moving back out. So we need to recognise then, so you've got your sodium, which is being actively moved out, but the sodium is not able to then flow back in because of the fact that this channel is shut. However, the potassium, which is moved inside, is able to move back out, and potassium holds a positive charge. So we've already got a situation where by the movement of the exchange of sodium and potassium, we had a -1, and that's going to be happening, and there'll be a summation of this with all of the different sodium potassium pumps which are pumping. And then we've got the outflow of potassium, which is then going to further increase the negativity and the relative negativity across the cell membrane and build up that potential difference. Our fourth factor are negative ions, which are permanent and sitting on the inside of that membrane. So we're going to just put in some of these permanent negative charges which are there. So just to summarise for you, in order to set up the -70 potential difference across the cell surface membrane, there are 4 key factors that are maintaining this. So number 1 is the sodium, potassium pump. In addition to that, we have the fact that your voltage gated sodium channels are shut. Your voltage gated potassium channels are open. And then finally, number 4 is that you have got permanent negative ions inside your cell. So the culmination of all four of those factors leads to the potential difference and that resting potential of minus 70 millivolts. And as we said at the beginning, this is really important because this is the state at which the cell membrane is able to be stimulated.